This is lesson 7.1, multiplying and dividing rational expressions. Our learning objectives are to determine the values for which a rational expression is undefined, simplify rational expressions, multiply rational expressions, divide rational expressions, and multiply and divide rational functions. Great, let's define what a rational expression is. A rational expression is an expression of the form p divided by q, where p and q are polynomials and q does not equal 0. So let's break that down. A rational expression is just a fraction. In fact, the word rational begins with 5 letters called ratio. All right, so when we talk about something that's rational in math, we're talking about a fraction, something that creates a ratio. And in this case, this rational expression is some polynomial that's on top divided by a polynomial that's on bottom. And we're saying q cannot equal 0 because you can't have 0 at the bottom of a fraction in the denominator. Okay, that's undefined. We've said that in the past. So we're dealing with rational expressions in this lesson, and we're learning how to multiply and divide them specifically. Now, let's first discuss how to determine the values for which a rational expression is undefined. So there's a two-step process, really short. Step 1, set the denominator equal to 0. And then step 2, solve the equation for the variable in question. All right, because like we said, the denominator is not allowed to equal 0. And so we're going to find the values for which a rational expression is undefined by taking each denominator of the fraction, setting it equal to 0, and solving for the variable. All right, I'll show you how it's done. So here's a rational expression. It's a polynomial divided by a polynomial. All right, in fact, it's a monomial divided by a monomial. And I only look at the denominator and I say, well, what causes the denominator to equal 0? And I solve it for the variable. In this case, I divide 3 from left to right, and I find out that, c is equal to 0. Okay, so if c equals 0, that is the value that will cause this rational expression to become undefined. So c, in fact, is not allowed to equal 0. So I like to put a slash through that equal sign. I put a slash through it saying c cannot equal 0 because that's what would cause it to be undefined. Let's look at another example. Here's another rational expression. It's a binomial divided by a binomial. And I look at the denominator, and I don't even need to look at the numerator. I don't even look at the numerator. I only focus on the denominator, and I set it equal to 0. So I have 2b plus 5 equals 0. Okay, what value of the variable b would cause this all to equal 0? Well, we can solve it for b. So I subtract 5, and I get 2b equals negative 5. And then I divide by 2, and I find out, yeah, b equals negative 5 halves. That is the value of b that would cause the denominator to equal 0. So I'm going to put a big slash through it and say b is not allowed to equal negative 5 halves. That's the only value that b is not allowed to be. All right, let's look at this third example. I have a binomial, and it's divided by a trinomial. This is a rational expression. It's a ratio or a fraction of two polynomials. So what I do is I take the denominator and I say, well, it equals 0. Let's let it equal 0. Okay, and so there I have it. The denominator has been set equal to 0. And then I think, well, how would I solve this for the variable x? And I get out my factoring skills. All right, and you're going to get out your factoring skills a lot in the coming lessons. So it's a good thing to practice. Right now, so I'm going to factor this trinomial into two binomials. And I'm going to pick two values that multiply to make 6, but they sum to make 5. And, well, what would that be? I've got it. 2 and 3. The values 2 and 3. 2 times 3 is 6, and 2 plus 3 is 5. So they're the values that will work in this case. All right, and now that I have factored this trinomial expression, that is now set equal to 0, I'm going to use the zero product property to say that, well, this x value is -2 because -2 plus 2 is 0, and this x value is -3 because -3 plus 3 is 0. So the solutions for the x value are -2 and -3, but then I put a slash through it because I have to say, well, these are the values that x is not allowed to equal, because if it did equal those values, then the denominator would be 0, right? It would be 0. Okay, so this is how you can determine the value for which a rational expression is undefined. And really all I did was follow this quick two-step process. Set the denominator equal to 0 and then solve the equation. That's it. Really simple. Little reminder for you, I did not even consider looking at the numerators for any of this information. So let's cross them out. I ignored the numerators. I don't even worry about them. They don't have any influence. I only am looking at the denominators, setting them equal to 0 and solving for the variable. Great, I hope that's helpful for you in understanding how to find values for which a rational expression is undefined. Let's move forward, and we're going to talk about simplifying rational expressions right now. That's our next objective. Now, a simplified rational expression. Okay, a rational expression is simplified if there are no common factors in its numerator and denominator. And I've put a little note here for you. You can cancel factors. You cannot cancel terms. Okay, so terms, they're not allowed to just cancel on the top and bottom of a fraction. But factors, they are allowed to cancel. Okay, so it's very important that you know this, and I'm going to show you an example of that coming up here. Now, how do you simplify a rational expression as far as possible? How do you fully simplify? Follow this quick two-step process. Step 1, factor the numerator and denominator completely. Step 2, simplify by dividing out common factors. Now, I have something for you. If you end up canceling terms instead of factors, okay, if you make the mistake of canceling terms instead of factors, then there will be a cute kitten that dies somewhere in this world. All right? So just imagine it. You're going to try to cancel some terms, and when you do that, a cute kitten dies somewhere. Now, if you cancel factors, okay, then that's okay. No kitten dies. Please don't kill kittens. Okay, we need them to live. So let's go ahead and look at what I'm referring to. Here's example 7.2, and it says simplify x squared plus 5x plus 6 divided by x squared plus 8x plus 12. And some students will look at this and say, well, look, there's an x squared and it's divided by an x squared, and so I'm going to cancel this with this. And if you do that, then you kill a kitten. And don't do that. That's not okay. So you cannot just cancel terms when you see them. Like terms are separated by addition and subtraction. You can't just cancel terms. That's illegal. Okay, but what you can do is you can factor the top and the bottom of this fraction. These two trinomials can be both factored, and let's see if they share common factors on top and bottom. Okay, so we're going to go ahead and factor this, and so I'm setting it all up. You're using all those factoring skills you gained in chapter 6. We're now in chapter 7. So I see x squared plus 5x plus 6, and I say, well, that's, going to factor to x plus 2 times x plus 3. And I see x squared plus 8x plus 12, and I say, well, that's going to factor two numbers that multiply to make 12, but sum to make 8. That's gonna be 2 and 6, right? So I do an x plus 2 and an x plus 6. By the way, remember, it doesn't matter what order I wrote them in. I could have written x plus 3 times x plus 2 on top and x plus 6 times x plus 2 on bottom. It doesn't matter the order with which I write them. But what you will notice at this point is that there are factors. There is a factor that's the same on top and bottom. This x plus 2 is the exact same factor as that x plus 2. Factors are the same if they have the same values with the exact same signs. Everything's got to be exactly the same, right? So x plus 2 can't cancel x minus 2, but x plus 2 can cancel x plus 2. There you go. So this is what I mean by up here, this phrase that I gave you. You can cancel factors, but you cannot cancel terms. right? So what would have been illegal? Canceling x squared with x squared. That's illegal. But once you factor everything, you can cancel factors that are multiplied, right? So these are the factors multiplying other stuff, and they can cancel. That's just fine. And so the final result of, the stuff that I just did, this trinomial divided by this trinomial, since these factors cancel, it's just x plus 3 divided by x plus 6. And I have now canceled. Now, some of you, again, you're going to be tempted and you're going to say, well, look, I've got an x and I'm going to cancel it with that x on top and bottom. And if you do that, you are killing another kitten. Another kitten just died. Do not do it. Okay? Actually, this is where it stops. Okay? This is it. Because we can't cancel terms, but we can cancel factors. I hope that this helps you to not make the common mistake that every algebra student makes at this point. So let's go ahead and try another one just to get you even more comfortable with it. So when I see this rational expression, right, a polynomial divided by a polynomial, a fraction of polynomials, great. I think in my brain, well, I need to factor the top and I need to factor the bottom. And when I look at the top, I see a GCF. I see 3 as the GCF. Okay, so I factor out a 3 and I get an a squared minus 4ab plus 4b squared. Okay, that's what I get. So I factored out a GCF. Great. Maybe there's more factoring that I can do, but we'll try that in a second. On the bottom, I look at the bottom and I say, well, 6a squared minus 24b squared. I see a GCF of 6. So I'm going to factor out a 6, and I'm left with an a squared minus 4b squared. Great. So I make it to this point, and then I ask myself, can I factor these things even further? And the answer is yes, I can. So I'm going to take it further, and I noticed a couple of patterns. Like this pattern right here, this trinomial, it's a perfect square trinomial. And this binomial right here, it's the difference of squares. Okay? So I'm going to factor further, and let me do that. So this perfect square trinomial, it factors to a minus 2b squared. I'll show it to you. This factors to a minus 2b times itself, which I can, maybe I'll just write it out like that. I'll write it out twice. So you're asking, how did you know that? Well, we in a previous lesson discussed how to factor perfect square trinomials. Please refer back to that if you have more questions. That's back from lesson 6.3. Now I see in this binomial here the difference of two things that are squared. And what's being squared? Well, a is being squared. And, well, this 4b squared, I can rewrite it as 2b squared, right? Because when I take 2 and I squared, that becomes 4, and then b and I squared, b squared, 4b squared. Yeah, so you can turn 4b squared into 2b in parentheses squared. Great, so now I have the difference of two things that are squared, and you have learned about the difference of squares. That factors to a plus 2b. Let me fix that. So that factors to a plus 2b times a minus 2b. Okay, so I have just gone through the factoring process, right? I first factored out 3 on the top and 6 on the bottom. And then I saw a trinomial on the top that was the perfect square trinomial, so I factored it. And then I saw the difference of squares on the bottom, so I factored it. And at this point, the only thing to do is to look to see if any factors cancel. So I look and I say, well, a minus 2b, it cancels a minus 2b on top and bottom. And also I see a fraction of 3/6, which I can reduce. I can reduce 3/6 to become 1/2, right? So any coefficient values, I can reduce them. And you might be tempted to try to cancel a minus 2b with a plus 2b, but these are not the same factor. They have opposite signs. You cannot cancel them. Okay, so I'm going to write our final result. So my final result of the work that has happened is 1 times a minus 2b. So I just get the a minus 2b on top because it's multiplied by 1, which doesn't change anything. And then on the bottom, I have a 2 times a plus 2b. And I'm just going to leave it like that. That is as simple as I can get it. And I leave it in factored form. Okay? So this is everything that I was able to do, everything that I was able to cancel. So you saw my work. I was able to cancel these factors, and I was able to reduce this fraction. Great. Now's a good time to bring up opposites in a rational expression. So let's define what opposites in a rational expression are. The opposite of a minus b is b minus a. All right, they're opposites of each other. And if I ever have a scenario where I encounter a minus b and it's divided by b minus a, then those opposites are equal to -1. That all simplifies to -1. Okay? And so an expression and its opposite divide each other to become -1. Now, when I encounter something that looks opposite from what I'm used to, I can factor a -1 out of it to make it kind of reverse direction. And I'll show you an example of that in example 7.4. So I see this trinomial divided by a binomial. And so I've got a rational expression, right? A polynomial divided by a polynomial. It's a fraction of polynomials. And so I'm going to try to start to factor. Okay, so in the top of this fraction, I've got a trinomial that I can possibly factor to 2 binomials. And it looks like a pretty easy trinomial to factor, so I put x and x at the beginning of each binomial. And I think which two numbers multiply to -32, but sum to -4. So you would think of all the factors of 32, like 1 and 32, 2 and 16, 4 and 8. And I get to 4 and 8 and I say, wait, 4 and 8 can sum to make -4 if I play with negatives, right? So if I have a -8 and a +4, that works. All right. So -8 times +4 is -32, and -8 plus 4 is -4. So this is why this factoring works for this trinomial. Great. Now I look at the bottom, and it looks backwards from what I'm used to. Usually we put the quadratic term first and the constant second. And so if I want to, I can factor out a -1 from that stuff and then reverse the direction of those two terms. So instead of 64 minus x squared, I can write it as x squared minus 64 if I factor out a -1. Great. Well, now I recognize this binomial as the difference of squares because 64 can be rewritten as 8 squared. So I've got the difference of squares, and in the past, in section 6.3, you worked on factoring the difference of squares. Okay, so it should come as no surprise that the bottom is, well, -1 times x plus 8 times x minus 8. This is the factoring of the difference of squares. What we do is we take the bases x and 8. We put x and 8 and x and 8 in two binomials, and then we separate the two terms with opposite signs, addition and subtraction. These two binomials are called conjugates. When you have the same term with the opposite signs, they are conjugates. Well, what's so nice about all of this stuff that I just did? Well, what's so nice is now that I have fully factored, I see that there's a factor x minus 8 on top and bottom, and so those end up canceling each other. Okay? So those were the only factors in the top and bottom that were in common. Now, if I look back at the original problem, some of you might have been tempted to go like this: x squared kills x squared. And if you try to do that, you just killed a kitten. Don't do that. Stop. So now we move forward, and all we have to do is clean this stuff up. And I've got an x plus 4 factor on top, and that's divided by an x plus 8 factor on bottom. And then this negative 1 right here, right? A negative, the funny thing about a negative sign in a fraction is it could be on the bottom, or it could be on the top, or it could be pulled to the front. So what I'm going to do is I'm going to take that negative sign, I'm going to pull it to the front of the fraction. This is oftentimes the cleanest way to get it done. And then I am done. This is it. And some of you, of course, will be tempted to kill a kitten at this point, and you're going to try to do, oh, x and x, they kill each other. No, you cannot cancel terms. Do not do that. Stop. Okay? So I'm trying to be very clear with you what the big mistake is that students make. Don't make that mistake. You're going to kill a kitten. Okay? There you go. Now let's go ahead and move forward into multiplying rational expressions together. So what if I have two rational expressions, like in this example 7.5, and here's a rational expression, and it's multiplied by another rational expression? How do you handle that? Well, that's what this section is for. We're going to work on multiplication of rational expressions. So if P, Q, R, and S are polynomials where Q does not equal 0 and S does not equal 0, then P over Q times R over S equals P times R divided by Q times S. This is the same thing that we're used to from like basic fractions in the past. Like if I just had numbers, like 1/2 times 3/4. How did we multiply two basic fractions together? Well, what we did is we multiplied the numerators together, 1 times 3, and that gives you 3. And then multiply the denominators together. 2 times 4 gives you 8. And so that resulting fraction is 3/8. And this is no different when I'm dealing with polynomials. Great. So here's a quick 3-step process of how you can multiply rational expressions together. Step 1, factor each numerator and denominator completely, guys. We need to factor everything. Okay, that's top left factored, bottom left factored, top right factored, bottom right factored. You're becoming factoring professionals, guys. Now, step 2, multiply the numerators and denominators together. Step 3, simplify by dividing out any common factors, and then you'll be done. Let me show you this in action. Okay, so here I see this rational expression, right? This polynomial fraction multiplied by another polynomial fraction. And so I think immediately to factor everything. So I start with the top left. And I say, well, what does 2x factor to? Well, it doesn't factor any further than 2 times x. That's what it is. It's 2 times x. And then the bottom, I factor the bottom left now. So can I factor this trinomial? Let me try. So I create two binomials, and it's just x squared to start with. So I know that the two binomials start with x and x. Why? Because x times x is x squared. And now I think of what are the factors of 10? And that's 1 times 10 and 2 times 5. And which one of those factors makes 7? Well, 2 and 5 do. So I'm going to put a plus 2 and a plus 5. And why did I choose plus signs? Because, well, in this case, it's a plus plus scenario, so I didn't have any negative factors to worry about. It was great. Let's move on. And so now I'm multiplying by another ratio of polynomials. And in this case, it's x squared minus 9. And you may immediately now notice that's the difference of squares, because 9 is 3 squared. So oftentimes it might be good for you to say, oh, 9 is 3 squared, so that you can see the difference of two things that are squared better. Anyways, you create two binomials, and you put x in the beginning of each one and 3 at the end of each one, and then you use opposite signs to factor the difference of squares. There we go. We have just factored the difference of squares. And lastly, we see this 6x squared. Now I can write that 6x squared as, like prime factorization. Like 6 is 2 times 3, and x squared is x times x. This helps me see everything like more clearly. Okay, so if you find the prime factorization of these basic things like 6x squared, 2x, there you go. Now that we have factored everything, right? That's step 1. Factor each numerator and denominator completely. Now we can move on to step 2, multiplying the numerators and denominators together. And then step 3, simplify by dividing out common factors. In fact, a lot of people like to, at this point, divide out those common factors out of the top and bottom of the fraction. So that's what I'm going to do. I'm going to hop in here and I'm going to kind of look at things and say, well, I see a 2 that the top and bottom share in common. See, this is a factor that the top shares with the bottom. And x is a factor that the top shares with the bottom because everything's factored at this point. Okay, and then I kind of just try to look a little further and see, is there anything else that cancels? And the answer is no, nothing else cancels at this point. And so I'm all done and I'm ready to write my final result out. And so what is my final result? Well, it's just gonna be x plus 3 times x minus 3, like, everything that's left. X plus 3 times x minus 3 on top, all divided by, well, a 3 times an x plus 2 times an x plus 5. And I can leave my final answer in this factored form. In fact, it's a very nice form to leave everything in, okay? And we're done. And, if you at this point made a decision that I'm going to, cancel this x with this x and this 3 with this 3, well, that's illegal. You just killed kittens. Don't do that. Stop. Thank you. All right, so here we go. Example 7.6. And now we are going to factor the top left, top right, bottom right. Let's go ahead and move a little faster at this point. So when I see these values, I factor everything, and I'm going to set things up really nicely for myself with the factoring. I'm going to create some binomials here. In fact, I know the factoring of all of these things will end up with two binomials for each top and bottom. Okay, and when I see 3a squared minus 8a minus 3, I quickly decide to factor that, and it gives me 3a plus 1 times a minus 3. Great. So I've just factored that top left. Now I'm going to move on to the bottom left, and I see the difference of squares, right? A squared minus, you could, turn the 25 into 5 squared to help you, but this is the difference of squares. So I put a and 5 and a and 5, and I separate them with a plus and a minus. Done. We factored the difference of squares. Moving to the top right, I see a squared, so I put a and a at the beginning. And then the factors of the c value 25 are 1 and 25, or 5 and 5. I know 5 and 5 makes 10 when you sum them, and they make 25 when you multiply them. So there we go. I've got a plus 5 times a plus 5. In fact, this was a perfect square trinomial, everybody, that we just factored. Perfect square trinomial. And then bottom right, I see that, and I think for a minute, and I just use my factoring skills from chapter 6, and I decide that's 3a plus 1 times a minus 5. Okay, so I am done. I've completed all of my factoring, and now that I've factored everything, now's the fun part, because I'm going to be able to cancel everything I see on top and bottom, because everything's in terms of factors now, not in terms of terms. So you see this 3a plus 1? It's on top and on bottom, so they cancel. And you see this a plus 5 on the bottom? Well, there's an a plus 5 on the top, and those cancel. And that's everything that cancels. Nothing else cancels on top and bottom. So I'm going to write my final answer, and I'm going to say, well, my final answer is a minus 3 times a plus 5 divided by a minus 5 times a minus 5. But you see, that's the same factor multiplied by itself. So I'm going to say it's a minus 5 squared. That's the simplest way to write it. A minus 5 times itself is a minus 5 squared. Great. So there we go. We have now written the final answer, the simplified answer. to the multiplication of two rational expressions. Great job. All right, so at this point, you're probably thinking, man, I need to be really good at factoring as a student. And that's exactly right. So those were the skills you gained in chapter 6. If you feel like you need to go back and gain those skills, please feel free to go back to chapter 6 to study through those. Great, because now we are going to, instead of talking about multiplying rational expressions like we did up here in these two examples, we're going to talk about dividing rational expressions. So how do you divide two rational expressions, one from another? And so here's a quick definition. If P, Q, R, and S are polynomials where Q cannot equal 0, R cannot equal 0, and S cannot equal 0, then P over Q divided by R over S equals P over Q times S over R. Now, you may be wondering, well, what in the world's going on here? Well, there's something we've discussed in a very early stage of this course, and that is keep, switch, flip. Okay, so you may remember a quick discussion that we had about keep, switch, flip. And what we're doing is we're keeping the first fraction the same, P over Q, you see. And now we're switching the division to multiplication. Okay, so we're going to make a division problem become a multiplication problem. And to do that, we have to flip the second fraction. So the R over S, we take its reciprocal, flipping it. So it becomes S over R. Okay, so keep, switch, flip. And by doing that, the division problem becomes a multiplication problem, which we already know how to do. All right, so we always turn division problems back into multiplication problems because we already know how to do those. All right, let me show you an example of that happening, some examples. But first, here's a quick 4-step process on how to do this. So step 1, rewrite division as the product of the first rational expression and the reciprocal of the second. That's the keep, switch, flip stuff. Step 2, factor the numerators and denominators completely. Step 3, multiply the numerators and denominators together. And step 4, simplify by dividing out common factors. So these steps are the same as the steps for multiplication, right? The exact same steps. But there's a step at the very beginning to do the keep, switch, flip stuff. All right, so let me show you an example. This example is 7.7. And yes, we're going to have to factor everything that we see. But while we do it, we have to keep, switch, flip. All right, so I'll show you that process. So example 7.7, I encounter it, and I say, well, I'm going to just start factoring the first fraction. And you may notice that this is the difference of cubes. So we're going to use the factoring pattern that you learned for the difference of cubes right here. And so I would take P and Q and put subtraction between them because this is the difference of cubes. You learned factoring patterns of the difference of cubes and the sum of cubes in section 6.3. Please go back and refer to that if you don't remember. All right, so now what we do is we take each of these terms, P and Q, and we square them. Okay, so this P, I'm going to take it and I'm going to square it, P squared. And then I take this term Q right here, and I square it and I put it at the end. So Q gets squared. And then in the middle, I put the two terms multiplied together, their product, P times Q. All right, so P times Q, it gets multiplied right there. And now the signs that happen here are, we call it SOAP, same, opposite, always positive. Well, same as the sign here. So this is the difference of cubes. So I put the difference sign here, same. And then I put the opposite sign here. So it becomes addition. And then the last sign is always positive. It's always a plus sign. There you go. So I just factored the difference of cubes. Here is the factoring. Now I look at the bottom and I say, well, look at this. This has, well, a GCF of 2. So I'm going to factor out a 2. And then I'm left with P squared plus PQ plus Q squared. There you go. Okay, now I get done with the factoring of the first rational expression, and I'm going to now switch division to multiplication. So this division, I'm going to turn it into multiplication right here. And then I'm going to take the reciprocal of the second fraction. So this bottom, I'm going to write the factored version up top. And 6, I can write its prime factors as 2 times 3. So I'm rewriting 6, that's on the bottom, on the top, as 2 times 3. And then I look at the top here, and it's p squared minus q squared. That's the difference of squares. So I quickly factor the difference of squares by creating two binomials. And I put p and q and p and q, and I put opposite signs between them, plus and minus. Great. All right, well, guess what? We just did the process of keep it, switch it, flip it, while we also factored. So I was doing both at the same time. And now that was the hard part. Now comes the fun part. Because it's fun to cancel factors. So we hop in here and we say, well, what cancels? And if you say p minus q kills p minus q, you are correct. Those are factors that cancel. And if you say, well, 2 kills 2, you are correct. Those are factors that cancel. And if you say p squared plus pq plus q squared kills p squared plus pq plus q squared, you are also correct because those are factors. And so the only stuff left is a 3 on top. That's the only factor left on top is the 3, right? This 3 right here didn't get canceled. And then on bottom, this p plus q, it did not get canceled. So I put p plus q, that factor on bottom, and this is the final result. It can't simplify any further. That's as far as it goes. Good job. All right, well, division problems don't always look like this type of division sign. Sometimes you have a rational expression divided by a rational expression that looks like this right here. So look at this. This is a rational expression divided by a rational expression. So instead of using this division symbol, we're using the big division symbol, right, of a big fraction. And so the process is the same, though, because we're going to take this stuff and we're going to keep it. And then we're going to take this division sign in the middle of everything, and we're going to switch it. And then we're going to take this bottom stuff, and we're going to flip it. All right? And that causes this division problem to become a multiplication problem. And in fact, I'm going to also do one more thing. I'm going to factor as I go, okay? So this whole thing, I'm going to take the top fraction. I'm going to keep it the same, but I'm going to factor it as I go. So I'm looking at the 6x squared minus 7x plus 2 stuff. And I'm saying, well, what does that factor to? And with, the factoring skills that you have gained, you decide, well, that's going to be 3x minus 2 times 2x minus 1, right? This right here is the factored version of this. And now I go down and I factor this, 4x minus 8. And, I see a common factor. The GCF is 4. And I have an x minus 2 left. Great. So now I have factored this piece. So it looks like this. So I kept this stuff the same, but I factored as I kept it. And now I'm going to switch this division sign to a multiplication sign. There's the switch. And now I'm going to what am I multiplying? Well, that bottom fraction I'm multiplying. Okay. But as I factor this stuff, the bottom gets flipped to the top, and the top gets flipped to the bottom. So I've got to flip these, taking the reciprocal. So I'm going to factor x squared minus 5x plus 6 on the top. And x squared minus 5x plus 6, well, that factors to x minus 2 times x minus 3. There you go. And then I'm taking the 2x squared minus 7x minus 3 stuff. Okay, and I am going to factor it. But I'm gonna flip it to the bottom of this fraction now. And that ends up giving me 2x minus 1 times x minus 3. Great. So I'm done. I have completed the keep switch flip and the factoring. And so now I'm going to cancel any common factors on top and bottom. And I look at it for a second, and I see a 2x minus 1 that cancels on top and bottom. You see the 2x minus 1 factor cancels. I also see, what else do I see? X minus 2 cancels on top and bottom. And I also see x minus 3 cancels on top and bottom. All right, so these are all of the factors that cancel. That's really satisfying, right? Because I have just simplified this expression, this rational expression. So the only factor left on top is the 3x minus 2, and the only factor left on bottom is the 4. And this is the final result. So we have divided this, this gross-looking polynomial fraction by this gross-looking polynomial fraction. But because we're so good at factoring, things simplify and look a lot simpler, right? Look a lot easier than they did. We should try another one, but this time we have 3 rational expressions multiplied or divided, right? So here I have a rational expression. It's multiplied by another rational expression, which is divided by this rational expression. Remember, when you hear rational expression, in math, rational just means it forms a ratio. A ratio is a fraction. And what are we talking about? A fraction of polynomials. There you go. So looking at this, I'm going to just start factoring. But whenever I see division, I'm going to do the keep it, switch, and flip the fraction on the right of the division symbol. So when I see the division symbol, I turn it into multiplication, and I take the reciprocal of this fraction. But I'm going to factor as I go. So let's just start by looking at the top left stuff. 3x minus 6, well, it factors to 3 times x minus 2, right? The GCF is 3, so we factored it out. And when I see 4x minus 4 on the bottom, I see I have a GCF of 4. And so I factor that out, and I'm left with an x minus 1. Okay, let's move on. We have multiplication of these trinomials on top and bottom. And so we're going to factor those trinomials quickly. And, we see they're simple trinomials to factor. And I have an x plus 3 here times x minus 1. That'll do the trick. And I have an x minus 5 times x plus 2 right here. Okay, so I've factored these trinomials. This one factors to this. This one factors to this. Stop and pause if you need a little time to think through the factorings of all this stuff. Now, this is where I switch division to multiplication. All right? So I'm doing a change of division to multiplication. And to do that, I take the reciprocal of this stuff. So I'm going to factor the 8x plus 16 that's on the bottom here on the top. And so I factor out the GCF of 8, and I get an x plus 2. And now I look at the top, and I factor it on the bottom. And so I see a GCF of 2, and I get x plus 6. Great. So I stop right there, and I say, well, I have factored everything. Is anything cancelable? Can I cancel anything? And so I just start jumping in and seeing what cancels. And so here I go with my canceling pen. I see an x plus 2 that cancels an x plus 2. I see an x minus 1 that cancels an x minus 1. Okay, I also see something that's reducible, like, this 8 and this 4. 8 divided by 4 reduces to 2 divided by 1. So I can take this 8 divided by 4 and turn it into the reduced fraction 2 over 1. Yeah, all of this is legit. And even this, look at this, 2 divided by 2. Well, now I can cancel this 2 with that 2. They're factors. Awesome. Well, this is everything that cancels. So I'm going to now write my final result. And I'm going to just combine all of the factors of the numerator together. So I see a 3, an x minus 2, an x plus 3. Those are the factors of the numerator. 3 times x minus 2 times x plus 3. And in the denominator, I see, well, 1 times x minus 5 times x plus 6. And, I make that 1 become invisible because 1 times anything is just that thing. So I'm making that the factor of 1, I'm making it become invisible to simplify the look of my final result. And here's my final result. And, some of you may want to try to cancel this x with that x or that x with that. No, don't do that. You just killed a kitten. No, we can cancel factors. We cannot cancel terms. All right. And I just have a couple final problems to consider. That's when we're dealing with rational functions. So these rational expressions can be rewritten as functions. Okay, a rational function is a function of the form r of x equals p of x over q of x, where p of x and q of x are polynomial functions, and q of x is not allowed to equal 0 because it's the denominator of a fraction. Okay, and we might name the function in question r of x because we're talking about a rational function, which begins with the letter r. So it's very common to call this function r instead of f. But we could call it f, it doesn't matter. Okay, now how do you determine the domain of a rational function? Step 1, set the denominator equal to 0. Step 2, solve the equation. And step 3, the domain is all real numbers, excluding the values found in step 2. Now, this is what we did on the very first example of this lesson. We set the denominator equal to 0, and we solved the equation to see which values cause the denominator to become 0. And in so doing, we found the values which cause the fraction to be undefined. Okay. So this is example 7.10. I'm going to go through this process. It says find the domain of r of x equals 2x squared minus 14x divided by 4x squared minus 16x minus 48. And so what I'm going to do is I'm going to set the denominator equal to 0. And so I just take the 4x squared minus 16x minus 48, and it is now equal to 0. Okay? So that's the first thing I do. Now that I set it equal to 0, I'm going to try using the zero product property by factoring the trinomial and finding the values that are solutions to this equation. And so I jump in here and I say, well, can I factor out a GCF? Well, there is a GCF. It's 4. And so I factor a 4 out of all of the terms, and I get x squared minus 4x minus 12. Okay, so first always look to see, is there a GCF? And then you can factor further. And can you think of two numbers that multiply to negative 12 but sum to negative 4? And you think for a second and you're like, wait, negative 6 and positive 2 do the trick. Negative 6 and positive 2, they will work. All right. And so we have now completed the factoring. And so what are the things that x is a solution for, right? What solutions are there for x? Well, this x is 6 because 6 minus 6 equals 0. So one of the solutions is 6. And the other solution is negative 2 because negative 2 plus 2 is 0. So this solution is negative 2. We have now found two solutions for x that cause the denominator to become 0, and so we put a big slash through the equal sign. We put a big slash through it because that means not equal to. X cannot equal 6 or negative 2 because they would cause the denominator to be 0, and so the rational function would be undefined. So the domain can be all real numbers. Sometimes we use a fancy R for all real numbers, except x cannot equal 6 or negative 2. This is the domain. All real numbers except for 6 and negative 2. Great. So that is how you find the domain of a rational function. You just take the denominator, set it equal to 0, and solve for the variable, and then put a big slash through the equal sign to say, hey, x cannot equal those things. But it can equal anything else, right? All real numbers except for those two values. So let's now move on, and we're going to try multiplying two functions together, two rational functions, and we're going to try dividing two functions one from another that are rational functions. And then we'll be done. So here's example 7.11, and we're going to take f of x and multiply it with g of x. And here f of x is defined as this rational function, and g of x is defined as this rational function. And so we will do that. And as I do it, I'm going to also factor. Like top left is 2x minus 6. So I'm going to factor out the GCF of 2, and I'm left with x minus 3. And now I'm dividing that by x squared minus 8x plus 15, which I will factor into, well, x minus 5 times x minus 3. And now I'm asked to multiply with the g of x function, which I will factor the top and bottom of. So I see x squared minus 25, and yeah, your brain immediately says, wait, that's the difference of squares, because it's x squared minus 5 squared. So you set up two binomials, and you put x at the beginning of each and 5 at the end of each, and then you put a plus sign and a minus sign, opposite signs there. And lastly, the bottom of this function is 2x plus 10, and so you see a GCF, right? You can factor out a 2, and you're left with an x plus 5. Great, we just factored everything as we multiplied these two functions together. And now we can see if any of the factors cancel each other. In fact, I see an x minus 5 that cancels an x minus 5. And I see an x minus 3 that cancels an x minus 3. And I also see a factor of 2 that cancels a factor of 2. This all cancels. But I also see an x plus 5 that cancels an x plus 5. Oh my gosh. Every term ended up canceling. That feels so good, right? And so what we get, when everything cancels, there's an invisible factor of 1 that appears, right? There's really a 1 times that stuff and 1 times that stuff in front. So when everything cancels, every term cancels, we end up with a 1 divided by a 1, which 1 divided by 1 is just 1. Okay, so that's the final answer. That feels really good. So yeah, sometimes every factor cancels on top and bottom, right? Boom, 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 boom. So everything canceled, and the answer is 1. That's awesome. Example 7.12, find r of x equals f of x divided by g of x, where f of x equals this stuff, and g of x equals this stuff. And what we're going to do is we're going to do a keep, switch, flip as I factor. So I'm going to factor and do a keep, switch, flip. So here I go. Let's keep the f of x function the same, but we're going to find its prime factors like this. Okay, so 3x squared is 3 times x times x. Yeah. When I see x squared minus 4x, I think, well, there's a GCF. The GCF is x, and so I'm left with x minus 4. Great. Now I'm going to change the division to multiplication. But when I do that, I have to take the reciprocal of the g of x function. And so what I'm going to do here is I'm going to factor the bottom, right? This bottom, it's now on top. And I'm going to factor x squared minus 7x plus 10. Well, that's x minus 5 times x minus 2. And then the top, I'm gonna flip it to the bottom, and I'm gonna factor it. And you know, when I look at that, I say, well, there's a 9x GCF. The GCF of these two terms is 9x. And what's left inside is an x minus 5. Great, I have now done a keep, switch, flip, and I factored everything. And now it's time to get out my canceling pen, my red canceling pen, to see, hey, what cancels? Well, the factor x minus 5 cancels the factor x minus 5. And I see this factor x kills, it cancels this factor x. And this factor x kills that factor x. And I see a 3 over 9. The factors 3 and 9, they are reducible, right? 3/9 is the same thing as 1/3. 1/3. So I can reduce that fraction. And that's everything that I can find that cancels. And so I will write my final simplified answer. And it's 1 times x minus 2 on top, which I'll just write as x minus 2. And what's left on bottom is x minus 4 times a 3. I'll write the 3 first. That's always good to do, to write the coefficient 3. The factor is just a numerical value, and I'm multiplying that with x minus 4. And that's my final result. I did it. So there you go. We have just practiced simplifying, multiplying, and dividing rational expressions, and then dealing with function notation, rational functions, right? Representing a function as a rational expression. Well, thank you so much. I hope you have a wonderful day, and I will see you in the next lesson.